He climbs until the engine starts to cough, a thread of silver smoke tugging at the exhausts, and a thin, mechanical cough that means the airplane is reaching for a border it cannot cross. Through his visor, he can make out the dark, distant blots of the formation ahead, 4, maybe 5 silhouettes cutting a pale sheet of cloud. Above them, the sky seems almost too clean, as if the air itself is a wall. The altimeter needles swing. His breath fogs the inside of the mask. He pushes the throttle forward, fingers white on the stick, and the needle creeps into the high 20s, then the lower 30s, altitudes that in the Pacific theater had become a new kind of sanctuary. At that height, the bomber crews sit in a warm, pressurized cabin, sipping coffee, adjusting charts. Below and around them, piston fighters find themselves chasing ghosts. Japanese aces chased the B-29 until its pressurized cabin put it 30,000 feet out of reach. This is the story of how an engineering decision, folded into mass production and operational doctrine, rewrote the rules of interception. It's a tale of pilots whose skill bumped up against the hard physics of thin air, and of an industrial machine that let its aircraft live where others could not. It is not a story of invulnerability. B-29s were far from immune, but for a crucial, growing stretch of the war, they occupied a vertical sanctuary that ordinary piston fighters could not reliably enter. If you like deep dives into World War II tech and tactics, subscribe. There are more layers below the surface. In the first moments after the climb begins, everything is intimate and immediate. The pilot's lungs, the engine's note, the thin hush as the world drops away. For the men and the fighters, there is a tactile catalog of warnings. The engine's manifold pressure starts to sag. Above a certain height, the carburetor and the supercharger no longer find enough dense air to generate full power. The propeller spins faster for less thrust because its blades bite at air that is progressively thinner. Instruments that felt steady at sea level become new riddles as altimeters and oxygen gauges flicker. The oxygen mask grows sweaty on their faces, the fogging amplifies the sense of dislocation. Cloud tops slip by like walls, and on the other side that matters, sit the B-29s, arranged with a confidence born of design. Picture a B-29 formation at dawn over the Japanese home islands in the summer of 1944-1945, distant, disciplined, and stubbornly high. The superfortress was conceived as a strategic, long-range bomber intended to operate at altitudes where enemy defenses and fighters would be less effective. One of its most consequential features was a pressurized crew cabin. Pressurization is, simply put, the creation of a stable, livable environment inside an aircraft while the outside atmosphere thins with altitude.
Instead of forcing every crewman to live the mission in the claustrophobic, choking environment of a pure oxygen mask, engineers sealed sections of the fuselage and mechanically maintained a comfortable internal pressure. The benefit is not merely comfort. It permits crews to operate complex systems, bomb sites, radios, gunnery stations, for extended periods without the physical drains that come from prolonged exposure to near-breathless conditions. For a fighter pilot, the difference is profound. A pressurized bomber can loiter where the air is thin, where human metabolism and engine performance begin to disagree, and do so with an endurance and operational efficiency that unpressurized crews cannot match. The B-29's pressurized compartments meant its bombing runs could be planned around an altitude envelope that made interception difficult for conventional fighters of the day. But pressurization was only part of the equation. The B-29 was a 4-engine aircraft with power plants and supercharging systems designed to make them effective higher in the column of atmosphere. Superchargers and turbochargers are devices that crank more air into an engine than would otherwise arrive naturally at altitude. In piston engines, power is the product of how much air and fuel you can combust on each cycle. As altitude increases, atmospheric pressure and air density fall. Without help, an engine's power drops off quickly. Superchargers, driven mechanically, and turbochargers, driven by exhaust gases, compress intake air to keep oxygen density up and preserve horsepower. The B-29 combined large displacement engines with supercharging systems sized to keep the bomber near its best performance in the low 30s, altitudes frequently described as around 30,000 feet. Japanese fighters, many of them remarkable machines at low and medium altitudes, were typically designed for different envelopes of operation. Early and mid-war Japanese designs emphasized maneuverability, range, and a light airframe to achieve an exceptional power-to-weight ratio at lower heights. The trade-off was that most lacked the kind of high-efficiency supercharging or turbocharging that would preserve engine output in the thin air above 20,000 feet. Some later Japanese designs and modifications attempted to address this, adding turbochargers or experimenting with high-altitude variants, but these efforts were piecemeal and arrived late in the war. In practice, by the time B-29s began to inflict strategic pressure deep into Japanese territory, the performance gap at altitude was real and operationally meaningful. Why does altitude matter? Because air is not just a medium for lift, it's also the engine's fuel-diluting partner and the propeller's working fluid. As density drops, both lift and thrust curves change.
A propeller becomes less efficient, losing the ability to accelerate a mass of air rearward. The wing generates less lift for a given angle of attack, and that means the fighter must fly faster or adopt higher angles that increase drag to stay aloft. Climb rate collapses even as fuel burn increases. A fighter that could reach 20,000 feet quickly and maneuver there could see its climb rate and controllability fall off sharply beyond that, turning an intercept into a gamble with time and oxygen as adversaries. The micro-anecdote, representative rather than singular, repeats through reports of the period. A Japanese pilot sees the bomber formation on the edge of cloud. He attacks, only to find his initial energy drained. He tries to climb to the bomber level. The engine sputters, or the propeller enters a regime of diminished bite. His oxygen mask becomes an additional hindrance, heavy, sweating, fogging that narrows peripheral vision, and he has to judge how long he can hold the attempt before fuel and altitude force a retreat. When a fighter climbs into thin air, the margin for error narrows. Misjudge the air density, and a high-angle maneuver can take you into a stall. Linger too long, and you may lack the fuel to return. Close too rapidly, and you risk losing sight of the bomber through cloud layers. In the Pacific, across the vastness of ocean and the jagged lines of archipelagos, commanders and pilots learn to see altitude as a theater of its own. It is tempting to reduce the story to hardware alone, B-29 specs against Japanese engine shortcomings, and to conclude that technology won outright. That would be a mistake. Human choices, training, tactics, and the war's logistics were all part of the interplay. A pressurized cabin did not make the bomber invincible. Anti-aircraft fire, radar-directed interceptions, night reconnaissance, and determined fighter pilots still pose threats. But what the pressurized B-29 did do was change the terms on which those threats had to operate. It required fighters to either accept a significant drop in performance to reach the bomber or force the air campaign to adapt in other ways. Consider the tactical calculus for an interceptor squadron leader assigning pilots to attack a B-29 formation. At lower altitudes, the rules are clear. Use energy tactics, boom and zoom attacks, coordinated fighters to attack from above and below, exploit transient blind spots. But at 28,000 to 32,000 feet, many of the conventional tactics have reduced utility. The fighter that reaches the bomber level is frequently marginal on fuel and engine margin. Its guns may still be lethal, but the time window and firing solutions tighten. A single pass may be all the opportunity the attacker gets. Defensive gunners in the bomber, protected by the superfortress's own trials in gunnery mounting and fire control systems, could respond in numbers larger than a lone attacker expected to face. Moreover, bomber commanders could choose altitudes and timing to minimize fighter exposure, cross a mountainous region, climb to cloud tops, or use the sheer distance to complicate any immediate scramble. Numbers help illustrate the systemic layer of this problem. The United States committed the B-29 to an industrial-scale program that produced these aircraft in significant numbers and sustained operations at tempo. By late 1944 and into 1945, B-29 formations mounted repeated raids, each sortie supported by logistical chains of maintenance crews, fuel, spare engines, and airfields capable of handling heavy four-engine bombers. The combination of pressurized cabin and higher service ceiling meant each aircraft, once repaired and fueled, could be used in a way that maximized survivability under the conditions of the Pacific theater. On the other side, Japanese industry, subject to material shortages, bombing, and shrinking logistical space, struggled to produce enough high-performance interceptors and the specialized equipment necessary to equal sustained high-altitude operations. These industrial realities translated to operational consequences. If an air force can put dozens or hundreds of aircraft into the air at an altitude band beyond most enemy fighters' comfortable envelope, it changes the attrition math. Fighters lose time and resources attempting to climb and intercept. Aircraft that do reach the band may suffer higher maintenance cycles after each attempt. Pilots who operate routinely near physiological limits require more recovery and suffer higher risk of fatigue and error. Meanwhile, the bomber force continues to operate with a different set of recoverable costs. If a percentage of missions achieve their objective because interceptors cannot consistently engage, then the strategic aim of the bombing campaign is served. But there is nuance. The war record includes both failed intercepts and successful engagements at altitude. There were Japanese pilots who pressed home attacks at the higher end of the flight envelope and who did so with bravery and cost. There were also experimental and late-war Japanese aircraft specifically modified or designed with turbochargers to improve high-altitude performance, efforts that demanded scarce resources and late, partial implementation. These examples demonstrate that engineering limits could be pushed. The issue, by the late stages of the campaign, was not absolute impossibility, but costly marginality. To understand the turning point, when many in the Japanese command and among frontline pilots began to accept that conventional interception was no longer reliably effective, we need to differentiate between isolated encounters and systemic patterns. Isolated victories do not invalidate a structural advantage. What matters is tempo and scale. If intercept attempts remain costly to mount and only sporadically successful, the bomber's altitude becomes functionally protective.
This is the moment the story hinges on. Not when one ace fails to reach a bomber, but when a pattern of failed or marginal intercepts accumulates into operational doctrine and planning. At the level of the individual pilot, the psychological effect was real and corrosive. Skilled aviators trained for head-on, dogfight encounters found themselves stripped of many habitual tools. The zen of close-range maneuvering, slipping and rolling to gain an angle, is a different art than the math of high-altitude climb in limited firing windows. Suddenly, the pilot's most trusted assets, rate of climb, instantaneous turn rate, the ability to trade energy for positioning, were conservative and unreliable. The result was frustration, improvisation, and in some cases, a reprioritization of mission objectives away from direct interception to other roles, trial engagement at lower altitudes, kamikaze missions in desperation, or shore-based anti-aircraft efforts. For bomber crews, pressurization offered operational advantages that reached beyond immediate survivability. Comfort and reduced physiological stress improved crew performance over long missions. A flight engineer could monitor engines without the constant interference of oxygen masks. Gunners could move between stations and coordinate with less physical strain. The ability to sit at an altitude that taxed enemy fighters but not your crew introduced an asymmetric endurance. The bomber could sustain its flight profile while attackers burned more fuel and approached physiological limits. All of this was amplified by the sheer scale of production and logistics the United States brought to bear. The B-29 program was a major industrial undertaking. New factories, supply chains feeding raw materials and engines, training programs producing crews, and maintenance depots rotating aircraft back into service. When technology and industry intersect, the result is not only an aircraft that can reach higher, but a force that can make the high altitude a persistent operating norm. For defenders, matching that requires not just a plane that can theoretically climb to the same level, but the industrial base to produce and maintain those interceptors in numbers and with reliability, plus the fuel and training pipelines to keep pilots ready for the special demands of high-altitude combat. What then did the Japanese forces do in response? The initial answers were tactical and adaptive. Night operations became more attractive. If daylight interception at altitude was marginal, then deprive the threat of light and shift the attack to hours when the bomber's navigational and bombing accuracy might suffer. Flak and searchlights were concentrated to create zones where the bombers might be forced lower.
There were attempts, as noted, to design or retrofit fighters with turbochargers, components that would theoretically return engine power at high altitude. But such programs require time, materials, and vulnerability to disruptions in supply. And, in the tragically complex calculus of late-war Japan, some responses sidestepped interception entirely. When the cost of countering massed bombing with the available means escalated, other desperate measures were adopted. But there's an intermediate phase between tactical stopgap measures and wholesale doctrinal shifts, a phase of reconnaissance and deduction in which air crews, intelligence officers, and operations planners try to quantify precisely what the new envelope means. They measure where the B-29 tends to fly, how its formation patterns evolve, and where their own fighters begin to lose margin. They collect reports, how many intercepts led to damaged bombers, how often fighters were lost trying to reach the altitude,
how often anti-aircraft defenses forced bombers down into more dangerous bands. This is the investigatory middle of the story, the workaday process of turning anecdote into doctrine. The narrative device that will carry us through this middle is the repeated, small-scale discovery, a squadron report here, a flight engineer's memo there, a pilot's after-action sketch that, when assembled, shows a vector, not a sudden epiphany, but an accumulation. It's the pattern that matters. One sortie where interceptors fail is a footnote. 10 sorties with similar outcomes become an operational problem. 100 such sorties expose a structural gap. So the scene broadens from the personal struggle in the cockpit into a more systemic one. In hangars and makeshift briefing rooms, technicians and commanders compare notes. Engine technicians describe recurring complaints about supercharger wear when the aircraft are pushed to maintain manifold pressures near their limits. Pilots testify to the vagaries of oxygen systems during extended high-altitude climbs, how masks slip, how radios cut out, how time above 30,000 feet or the equivalent strain affects judgment. Intelligence officers plot course and altitude, looking for choke points where fighters might exploit terrain or predict bomber routes. Supply officers calculate how many interceptors could be produced with effective turbochargers given available materials. The work becomes mathematical, forensic, and political. It is where engineering meets strategy. This is where a key tension emerges. Modifying fighters for sustained high-altitude performance is not a simple bolt-on change. Turbochargers and improved superchargers require redesign of engine installations, alteration of cooling systems, additional maintenance training, and often new aircraft capable of handling the stress and weight of the modifications. These changes ripple through production and deployment schedules.
Even if such upgrades are technically feasible, they compete for scarce resources in an economy already strained by blockade, bombing, and the demands of multiple fronts. The choice becomes not purely technical but strategic. Invest in a handful of high-altitude interceptors and accept vulnerability elsewhere, or allocate resources to a broader defensive network that does not rely on direct interception. While that debate unfolds in command rooms, the human dimension continues in the sky. On a cold dawn sortie, a B-29 pilot reports that enemy fighters dived from below, attempted head-on passes, or tried to exploit cloud cover. The bomber's gunners reply with flak and concentrated fire, and sometimes the tactics work, sometimes they do not. The fighters that made it within range often did so because of a favorable set of circumstances. The bombers were forced low, the formation was stretched, or the attackers found a gap. These exceptions prove the rule and keep the narrative honest. The high-altitude advantage was neither complete nor uniform. It was, however, consistent enough to shape operations. We now approach the moment where the accumulation of reports and the realities of production collide. Commanders and staff officers, surveying the pattern of sorties, losses, and the capabilities of their forces, faced a hard realization. To change the playing field required more than tactical tweaks. It demanded industrial parity or an operational choice that would circumvent altitude altogether. That decision set in motion a chain of adaptations, some immediate and tactical, others strategic and long-term. It is the hinge on which the rest of the story swings, whether to accept the attrition of strategic bombing as a price of fighting, to adapt air defense doctrine and focus on alternate denial measures, or to attempt to match the high-altitude performance through focused engineering programs. Each path carried costs and consequences. Before we trace those consequences in detail, it's worth returning to the visceral image that began this account and to the physical realities that drive it. The pilot at his stick is not merely fighting the bomber, he is fighting the atmosphere. The thinness of the air is an invisible foe, one that a pressurized cockpit has effectively immunized the B-29 against. The Superfortress's designers took steps to make high altitude a practical theater, and the American logistical system made those steps durable. For the interceptor, the climb is a transaction, time and fuel exchanged for a chance to inflict damage. In operational terms, when the expense of that exchange becomes too high in relation to the expected return, doctrine shifts. There is a small, decisive episode that crystallizes this pattern into a tangible realization among planners, an encounter recorded in multiple flight logs and echoed in the voices of crews. It is not a single famous dogfight with a named ace. Rather, it is a string of sorties over a focused period in which intercept attempts failed repeatedly because fighters could not maintain effective firing windows. Pilots reported losing sight of the bomber in cloud, or the bomber steamrolling above them as their engines retreated in power. Maintenance logs show repeated wear on supercharger components, strained beyond their design points. Intelligence tables tally escaped bombing runs and the comparatively small number of confirmed shootdowns achieved at altitude. The collection of these fragments, when laid side by side, produces an aha that is less dramatic than cinematic, but more consequential. Engineering and industry have, in effect, lifted these bombers into a different stratum of airspace, one that requires a different sort of response. As that realization sank in, tactical improvisations were tried. Some fighter units experimented with ground-controlled interception, vectoring pilots to predicted intercept points so they could climb less and intercept more opportunistically. Others adjusted patrol altitudes and timing to exploit moments when B-29s descended for weather or fuel reasons. Coastal and island defenses attempted to shape the bomber's approach path with anti-aircraft concentrations designed to force lower altitudes. None of these applications eliminated the core problem. They mitigated it in patches. Meanwhile, some planners pushed harder for engineering solutions, more robust turbochargers, redesigns of engine intakes, higher octane fuels, and stronger airframes. But as with the tactical options, each came with costs that had to be evaluated against the ever-shortening window of wartime resources. It is here, at this intersection of pilot experience, mechanical reality, and logistical constraint, that the narrative pauses and sharpens into a question. Confronted with an enemy that can operate comfortably where you cannot, what is the right mix of immediate tactical countermeasures and long-term engineering investment? The answer would not be uniform across the theater. It would vary with geography, supply, and political will. But the emergence of the pressurized B-29 as an operational sanctuary forced the question in new ways, and that is the axis around which the strategic story now begins to rotate. The next phase of the story moves from the tactical sketches and production tallies into the concrete adaptations, the specific engineering programs and tactical doctrines attempted, their costs, and their limited successes. It looks at how some units refined intercept techniques, how logistics sought to pivot resources, and how, in the larger sweep, industrial capacity, already an American advantage, translated into persistent operational leverage. That movement is where the hard lessons consolidate into doctrine, and where individual courage meets systemic constraints.
It is also where the cost of adaptation, human, technical, and material, becomes visible. Command rooms and maintenance sheds are where the temper of a campaign is often forged, and it was there, among pencil charts, greasy rags, and stacks of flight reports, that the implications of the B-29's altitude advantage hardened into policy. The initial answers were practical and immediate: change tactics, concentrate flak, try to force the bomber down. But the more strategic responses demanded engineering fixes that reached far beyond an individual pilot's skill. To retrofit fighters with the capacity to operate effectively in the low 30s of altitude required more than an add-on. It required time, materials, and a production base that could sustain the extra complexity. Those were resources Japan increasingly did not have. The mechanical reality of high-altitude aviation is ruthless in its demands. Adding a turbocharger or a more effective supercharger to a piston engine is not simply bolting on a new part. Turbochargers, driven by exhaust gas energy, compress intake air to restore manifold pressure as outside air thins. They permit an engine to breathe more easily where the atmosphere does not provide sufficient oxygen. But they also bring new heat loads, require reliable bearings and oil systems, and demand more meticulous maintenance. Superchargers, mechanically driven from the engine, rob some power to drive themselves. They improve top-end performance, but also change the vibration and cooling picture of an installation. In either case, the intake and exhaust plumbing must be rethought, firewall clearances considered, and the aircraft's center of gravity adjusted. Every modification that improves high-altitude performance tends to ripple into the supply chain. Different bearings must be stockpiled, new testing protocols written, trained mechanics brought to the field. In wartime Japan, those ripples struck hard constraints. Factories were intermittently damaged by air raids, access to high-grade alloys and precision machining was increasingly restricted, and fuel quality varied from ideal to improvised. The American industrial system that supported the B-29 program did not eliminate maintenance headaches, but it distributed those headaches across an enormous logistics machine: depots, spare engines, pool spares for turbochargers, and a flow of replacement aircraft that kept formations flying. For the Japanese technical teams, every turbocharger ordered was a gamble against supply disruptions, and every experimental high-altitude fighter committed resources away from the many fronts that demanded more conventional interceptors, trainers, or naval aircraft. Operationally, then, adaptation splintered into parallel efforts. On the one hand were programs to craft better interceptors.
limited production models or retrofits that on paper could regain performance at altitude.
On the other were tactical innovations. Better radar direction where available, predicted intercept plotting designed to place fighters along a bomber's projected track so that the climb was shorter or unnecessary, and concentrated anti-aircraft barrages set to make bombing runs more dangerous without relying on fighters alone. Coastal batteries learned to shape approach corridors with overlapping barrage zones so that bombers had to trade altitude for survivability. Night raids and the exploitation of weather windows became more attractive. If daylight interception at altitude was an asymmetric fight, then remove daylight from the equation and make bombing less precise, but also less predictable. These responses produced mixed results. Small numbers of modified fighters occasionally reached the altitude band and brought bombers down, proving that the engineering problem was not impossible. But the very scarcity of those aircraft and the intense maintenance they required made them marginal in the calculus of a sustained air defense. Interception became a matter of opportunism and luck as much as it was of skill. Where an Air Force could field a handful of specially outfitted interceptors, their value was undeniable, but they did not, in late-war Japan, constitute a systemic overturning of the bomber's operational sanctuary. The physiological toll on pilots operating near and beyond the service ceiling complicates the picture further. Even with oxygen equipment, the body does not respond kindly to repeated exposures near the edge of its designed envelope. Hypoxia is insidious, reaction time slow, visual acuity degrades, and complex judgment calls, target identification, firing solutions, navigation, become more error-prone. Temperatures plunge. Without specialized electrically heated flight gear, the cold reaches into the bones. Radios, delicate and dependent on stable power and antenna performance, become temperamental. The combat pilot who spent long hours at such margins returns not only with a report, but with fatigue that lowers unit readiness. For planners, the cost is not measured only in aircraft hours, but in the human capacity to sustain the intensity of operations necessary to blunt a massed bomber campaign. That human cost surfaced repeatedly in the operational records that filtered back to staff officers. Flight logs noted engines that blacked out under strain, oxygen gauges that dipped during long climbs, and patches of cloud that turned an intercept into a blind stab. Maintenance crews logged regular failures in high-stress components, supercharger bearings run beyond design tolerances, intercooler plumbing weakened by heat cycles, and airframes stressed by the repeated high-power climbs. These items, taken together, sketched a force structure ill-suited to the sustained high-altitude duel the B-29's designers had placed before them. Equally decisive was the strategic calculus that industry imposes upon war.
An economy can usually produce a few test beds of high-performance hardware, but changing the character of an Air Force requires output at scale. The United States shifted factories, retooled plants, and marshaled resources for the B-29 program in a way that made high-altitude operations routine for entire wings. Japan's capacity to pivot, either to produce large numbers of turbocharged fighters or to establish a matched logistical network, was constrained by several factors: loss of resource-rich territories, disruption of shipping lanes, and the sustained strategic bombing that hit transportation and manufacturing hubs. The result was not impotence on the battlefield, but a strategic squeeze. The defenders could innovate, but not at the speed or scale necessary to reclaim the air layer the superfortresses were exploiting. That squeeze turned doctrine inward. Where direct interception at altitude was marginally effective and costly, the emphasis moved towards shaping the battle space to deny the bombers freedom of action. Searchlight and flak systems gained renewed priority. Coastal warning nets and radar pickets, though sparse and imperfect, were better utilized to channel bomber formations into belts of lesser altitude. Operations planners accepted trade-offs, increased the acceptability of some bombing accuracy loss in exchange for more opportunities to bring the fight to the bombers at lower altitudes where interceptors were at less of a mechanical disadvantage. There were, moreover, consequences in terms of strategic risk assessment. Each nation must decide how to apportion scarce assets across competing needs. For Japan, dedicating more iron and labor to high-altitude interceptors meant withdrawing resources from fighters used for island defense, carrier operations, or ground support. For the United States, the investment in an aircraft that could ride higher and pressurize its crew paid dividends precisely because it dovetailed with a logistics model that could sustain large formations. In essence, the B-29's altitude advantage was not a single lever, but the product of design choices magnified by industrial policy. Amid these systemic evaluations, there were still moments of vivid human combat.
fighters pelting in beneath the bomber wakes, a lone attacker finding a seam in formation discipline, a gunner with a clear sight and a devastating burst. These episodes remind us that war is not solely a ledger of factories and specifications. The superfortress remained vulnerable to determined and skillful attackers, to radar-directed strikes, to weather, and to sheer chance. Yet what those individual engagements did not overturn was the structural pattern. Over many sorties and months, the bomber force's ability to operate at a higher envelope degraded the defender's interception efficiency sufficiently to influence strategy. The aha crystallizes not in a single filmic duel, but in the arithmetic of persistence.
Read the logs across a theater and the pattern emerges. Lower interception rates at altitude, higher maintenance demands for fighters attempting to operate there, a churning necessity to allocate scarce turbocharger components, high-octane fuels, and technician hours to a relatively small set of high-altitude attempts. Each of those pieces on its own is a technical annoyance. Stacked together, they become a strategic break. The cumulative effect, reduced effective interception opportunities, rising costs per attempted intercept, and a shrinking capacity to produce enough specialized hardware made altitude a defensive layer in its own right. That realization had consequences beyond the mechanics of flight. It affected morale, doctrine, and the allocation of human attention. Pilots who had trained and prepared for one style of combat had to recalibrate insofar as resources allowed. Commanders had to choose between immediate tactical fixes and long-term engineering programs that might not reach fruition before the strategic balance shifted again. For an attacker, the calculus of risk changed. To invest time and fuel and high climbs for the chance of a few critical hits, or to instead accept a defensive maritime and land posture that increased reliance on other denial methods. As the campaign matured, two other factors amplified the altitude advantage: the evolution of bomber formations and the refinement of their defensive systems. Formation discipline, fire control coordination among multiple gunner positions, and improved bombardier and navigator procedures combined to make single-pass attacks less decisive. The B-29's fire control concepts, linking guns and directors to concentrate defensive fire, meant that a lone fighter's chances of making a clean run without severe exposure diminished. In other words, the bomber did not simply sit above the fighters like an inert target. It presented a coordinated defensive front, optimized for the environment in which it chose to live. It is tempting when recounting these dynamics to set technology and industrial power against the intimate valor of air crews as though the contest were purely mechanical. The truth is more complicated, and in many ways more human. The men who climbed until their engines coughed, who jinked through cloud and fought for a fleeting sight of a bomber's tail, did so with courage and professionalism. Their struggle against an indifferent atmosphere, against the slow attrition of their machines, and against the wrenching decisions about resource allocation is part of the story. What changed was not their willingness to fight, but the terms on which fighting remained a rational choice. By late stages of the campaign, the aggregate effect of the B-29's operational envelope had become apparent to planners on both sides. For the attackers, it altered priorities. Where possible, invest in specialized interceptors or accept a higher emphasis on anti-aircraft measures and night defense.
For the bomber force, the altitude capability validated a doctrine of sustained strategic pressure delivered from a band of airspace that, while not sacrosanct, was operationally advantageous. In the calculus of war, certain envelopes of the atmosphere had effectively become protected zones, spaces defined not by sovereignty, but by engineering. When the dust settles on this specific chapter of aerial warfare, the lesson is not that machines alone decided the outcome, nor is it that individual skill did not matter. Rather, it is that engineering choices, when paired with the capacity to produce and sustain them, can change the geometry of conflict. The pressurized cabin was a human-centered innovation. It preserved the crew's effectiveness, but its operational consequence was to make a layer of sky into an asymmetric defensive resource. The B-29's designers had given its occupants not invulnerability, but a working environment in which the aircraft could habitually operate at heights that strained many contemporary interceptors. The closing image returns us to the fighter pilot climbing through a wash of cloud and thin blue air. He reaches the edge of where his airplane can breathe, and there, just above him, the bomber formation drifts with the calm of an aircraft built for that stratum. He has trained, he has skill, and he carries the same audacity that has produced aerial triumphs since the earliest dogfights. Yet in this moment, it is the physics of air and the economy of production, pressurization, dependable engines, logistics, that govern the odds. They are the quiet rules of engagement that matter as much as a pilot's decisions. The tactical adaptations, the limited engineering fixes, and the human efforts to overcome these constraints are all part of the same story. In the end, Japanese aces chased the B-29 across the Pacific sky, and in doing so, they encountered a new kind of limit. Not merely the limits of their machines or bodies in isolation, but the limits imposed by an opponent's ability to design, build, and sustain an aircraft that could live where others could not follow easily. That is the strategic point. Altitude became a layer of defense, and pressurization was the key that unlocked it. If this episode of aerial history left you wanting to dig deeper into how the B-29's pressurization and engine systems were engineered, and how those systems were sustained by the logistics that backed them, watch our next deep dive on the Superfortress's design and development. The link is in the description. If you found this analysis helpful, consider subscribing for more examinations of technology and tactics in wartime.